All right, so today we've got a continuation of the sets that we've been talking about. And today we're going to talk specifically about subsets. We're also going to talk about some set operations, and some Venn diagrams will kind of be thrown in there, but we're more going to do that in the next lecture. So let's go ahead and get started right off the bat. So let's start off with a definition of the complement of a set. So this word complement, we mean things that are not in the set. So let's say I give you a set here. Let's call it, well, I won't bother giving it a name. Let's just say that I've got in this set A, B, C, D, F, G, H, I, J, K, L. Notice I'm skipping some here. And just, this might seem tedious, but let's write them all out. I want to make a very clear point. So I've got almost all the letters of the alphabet here. You notice I've missed two. I've left out E and I've left out J. So if this is my set that I'm considering, my complement is going to be everything that's not in this set. And hopefully it's pretty clear that that complement in this case is going to be the set E and J, right? Because those are the letters that aren't in this set, right? But here's where things get confusing. What if my set isn't just letters, or what if it's not just numbers? What if it's a mix of things, right? So what if I gave you a set that looked like so? Dog, 2, W. Yeah, dog, 2, and W. Let's just use that. So I have dog, 2, and W. And I ask you what's the complement of that set. That gets a little weird, because what things are not in this set? Well, I don't even know, what am I talking about? I'm talking about all animals, all letters, and all numbers. I mean, that's a lot of stuff, right? And so what we generally have to do here is we have to define a universe. Let me write that out. So we'll say universe. We generally call this U. And so this is best shown with a picture. I'll get into this in a second. But this idea of the universe, it's everything that could possibly be in the set. So coming back here, in this example here, the universe would probably just be all of the letters in the English alphabet. And then the complement, okay, now I know which things are not in the set in the red, but are in the alphabet, boom, E and J. But here with this example, dog, 2, and W, I mean, what the heck is my universe? I mean, that's hard to come up with. So let's look at a definition, then a great picture that'll hopefully illuminate this idea of the universe, and then we'll do some examples after that. So the definition of complement, we've seen this, I'll repeat it. It's the set of elements that are in the universe that are not in the original set. So notationally, what we'll write is we'll write this prime, this little prime symbol. So that's right there, that A prime. So if I have a set A, we say that the complement is A prime. And using this notation that we saw a little bit last time, and hopefully you're a little bit more familiar with now, it's the set of x's such that all of these x's are in the universe that we're talking about. They're in the letters or numbers or whatever, or animals or something like that. And they're not in A, right? That gives us the things in the complement, those things that are not in A. Pictorially, what we've got here is we've got my entire universe in the green. I've got everything outside of the universe as well, I guess, just hanging around out here. Maybe I'm talking about, maybe my set in consideration, my universe, is all animals with 4 legs. Well, humans wouldn't be in that, because we'd be somewhere out here, because we don't have 4 legs, we just have 2. And so my universe is everything in the green. And then maybe I'm talking about So here, yeah, let me write these out just so we can keep these. So U is equal to four-legged animals. And then A is this set in red. And maybe this is something, it's not all four-legged animals, but it's four-legged animals that also have two eyes. There you go. And what we would say here is that A prime, everything in the green, so all of this stuff out here, all of that, everything out there, that's the complement of A. And what you could see is that everything out here in this green section, that's going to be a bunch of four-legged animals that don't have two eyes. I can't come up with one of those right off the top of my head. I'm not a biologist, but I'm sure there are some. There's some four-legged animals without two eyes. And that would be our A complement, our A prime, sometimes people will call it. And that's sort of a good pictorial example of this definition that we're seeing here, where it's all the elements that they're in the universe, but they're not in this set A, right? So they're everything here that I'm shading in currently. And that's that idea of a complement. So let's look at an example of this. Let's say I give you a universe and it's the numbers 1, 2, 3, 4, and 5. So those are the only 5 things you care about. We just care about these numbers here. And then I give you the set A and it's just the numbers 1 and 4. What I would do is I would put 1 and 4 in my circle, in my red circle, but 2, 3, and 5, they're outside the circle. Now notice they're still in this green universe, right? It's just that they're not in A, right? And so the complement is exactly that. It's those things that are not in A, but they're still in the universe. That's 2, 3, and 5. Let me be clear. I could also do something like this. I could put like 6 and 7 and 8 and 9. Those would be outside here, and 10, and I could keep going. Those are not in the universe that I'm talking about though, right? Because I've told you that our universe is 1 through 5 here. So I don't even care about 6, 7, 8, 9, 10. I don't care about any of those numbers. They're not going to be in my complement because they're not in the universe that I'm considering. So in these complement questions, I'm generally going to give you a universe. There are some cases where the universe should be fairly obvious, as in like it's all the numbers or it's all the letters. We did that example back here where I thought it was pretty obvious that the universe was everything in red, all the letters. It's the universe is all the letters in the alphabet. I misspoke there. I said the universe is all the stuff in red. That's not true. The set is everything in red. The universe is everything that we're talking about, which in this case is letters, and that's usually pretty clear. There are actually some examples as well where I don't give you the universe. Those are tricky. I'm not going to tell you those now because I'm going to ask you about them later, but just be careful. All right, so let's talk about subsets now. And when we talk about a set, we can talk about a part of that set, just a portion of it, right? And so let's just start off with an example before I even get to this definition. If I have a set 1, 2, 3, 4, 5, 6, 7, I can just take part of that, right? I can just take 2, 4, and 5. And if I wrote that out over here as 2, 4, 5, this is a set as well. But what we say is that this set in the green is a subset of that red set. And sort of definitionally, we say that if every element of one of the sets is also an element of the other, then that first set is a subset of the second. Let me say that again because that's confusing. And let me give these some names as well. So I've got B, and I've got A. So if every element in A, that's 2, 4, and 5, is also an element of B, and hey, look, 2, 4, 5. So that's true. Every element that's in A is in B. Then A is a subset of B. So here's a question for you. Is B a subset of A? So we ask ourselves, let's look at every element in B. Are every single one of these that I've underlined, are they in A? And no, they're not, right? Because 1, 3, 6, and 7, none of those are in A. So B is not a subset of A, but A is in fact a subset of B. So you want to be careful there in terms of the order and how you're saying it verbally. Notationally, we say A is a subset of B. This notation here means subset there. And that's just something to know. This notation means subset. We're going to break down this notation a little bit more. Basically, you can think about this symbol as being broken up into two parts. It's this tiny, like, sideways, cup looking thing, kind of like a C almost, and then almost like an equal sign, right? So this part here, it means subset of, and this part here, kind of like half of an equal sign, it means or equal to. This is very similar to like less than or equal to, or greater than or equal to, or something like that. This is just, it's a subset or equal to. So that's sort of that notation there. Yeah. Well, I was going to talk more about that notation, but I'm going to wait. We'll come back to it. So we've got the subset notation. A is a subset of B, very different from B is a subset of A. Let's look at some examples here. And this might be a tricky one. Is B a subset of A? Well, you look at these and you're like, wait, they're the same thing. So you would think, no, it's not a subset because they're the same thing, and subsets got to be smaller, right? I've got, I used this example before where I had, 1 through 7, and then I looked at like 2, 4, and 5, which was just a portion of it, and that was a subset. So right off the bat, this almost looks like, no, B is not a subset of A. It's the same exact thing. Well, let's look at the definition, okay? So the definition of a subset is that every element in B is in A. So let's go through. Red, is that in A? You go, yeah, it's right there. Great. Okay, let's look at yellow. Is that in A? Yeah, it's right there. Blue, is that in A? Yeah, it is. Right there. So actually, by definition, this is true. And in fact, A is also a subset of B. Let me add that in. Is a subset of B? Yes, it is. And that's, again, you got to just be careful there. Don't think intuitionally. Think based on that definition, right? Every element in B is in A, and then also every element of A is in B. That means that each is a subset of the other. So what we'll talk about now is actually this idea of a proper subset. And this is very related to that. It's very tied into that example. B is a proper subset of A if it's a subset, but not equal to it. So this example here, while we looked at definitionally, B is a subset of A because every element in B is in A. These are equal. These are equal sets. They're the same exact thing. So that means that B is not a proper subset of A. All right. And that goes back to this definition here. So the example with the numbers, the 1 through 7, and then the 2, 4, 5 that we had, that 2, 4, 5 was a subset of the set 1 through 7, and it also is a proper subset. But this example here, this is a subset, but it is not a proper subset. Notationally, what we do with a proper subset is we just write, let me use a different color here. We just write the cup part of that symbol. Contrast this with subset where we put that subset of or equal to, right? Let me swing back up here. This top guy means it's a subset of. This bottom part means or it's equal to. Well, if we just don't put this or equal to sign in there, we just get that. So I might say that, A is a proper subset of B. Try not to make that look like the letter C. Just gotta be careful there. All right, so there's proper subsets. So let's take a look at just a simple example here to distinguish between the difference of subsets and proper subsets. If I give you the set A and it's 1, 2, and 3, then my subsets are basically every little portion of it, right? I look at 1, the set just containing 1, and I ask myself, is everything in here in A? And I go, well, yeah, there's a 1 right here. There's a 1 up in A. I'm good. Same with 2, same with 3. And then I come down here to 1 and 2, and I say, okay, 1 and 2, are each of those in A? And I go, yeah, there they are. They're right there. Great. 1 and 3, are each of those in A? Yeah, they are. And I keep going down the line. I get to 1, 2, 3. And again, I keep asking myself, are each of these things in A? And I go, yeah, they're all right there. So that is a subset. Here's where things get a little tricky. The empty set, by definition, is considered to be a subset. Don't ask me why. There's reasons for it that are beyond the scope of this class. I kind of hate using that term, beyond the scope of this class, but it's true. There are reasons for it that we're not really going to talk about. Just remember that the empty set is considered a subset. So yeah, proper subsets, as we talked about, by definition, a proper subset is anything that's a subset but not equal to it. So all I do is I just don't count this guy, this last one where it's equal to, or it's the same set. So I just have one less. I'm just missing one of them. So here's some patterns I want us to notice. Well, I want to ask you guys, how many elements are there in A? You should say 3. I look at these, I go, hey, there's one element, there's second element, and there's a third element. So there are 3 elements here. And then I look at how many subsets there are. Let's count them up. I got 1, 2, 3, 4, 5, 6, 7, 8. And then as we saw, I have 1 less proper subset, so I have 7. What you should be able to tell, probably not just with this one example, but if you do a couple different examples, maybe try set B equals 1, 2. And try the set C equals 1, 2, 3, 4. There's a pattern here. And how this pattern works is that if I give you a set, so if I give you a set with n elements, so set has n elements. And let me do this in a different color, this n. So the set has n elements, then there are 2 to the n subsets. And let's look and see if that worked. There were 3 elements in A. So if I do 2 to the 3rd, that gives me 8, right? 2 to the 3rd. So if n is 3, then 2 to the n equals 2 to the 3rd. That's 8. That's how many we counted that there were. Last thing is there are 2 to the n minus 1 proper subsets. As we saw, there's always 1 less proper subset than subset. So I just take that 2 to the n, that 8, and I subtract off 1, and I get my 7. And that's exactly how many we counted on those proper subsets. So this pattern comes up. I recommend trying it. Write out all the subsets and proper subsets for this set B, and write them all out for this set C that I'm highlighting and circling here, and see how many, count them up, count how many there are, and I guarantee you it's going to follow this pattern where if your set has n elements, it's going to be 2 to the n subsets and 2 to the n minus 1 proper subsets. got all that written out right there. And so let's actually just do a quick example showing you why this last little formula is helpful. Let's say I give you the set A is equal to elements X such that X is even. And no, let's not say even. Let's say a natural number. X is a natural number and X is less than or equal to 8. This is going to be very annoying to write out all of these subsets. Let me be clear. This is the set that I wrote. I just didn't feel like writing 1, 2, 3, 4, 5, 6, 7, 8. But these are the same exact thing. They mean the same thing. I'm just writing them in 2 different ways. It's going to be very annoying to write out the subsets for this because you have the subset 1, you get the subset 2, the subset 3, and all down the line, just individuals. I've got 1 and 2. I've got 1 and 3. I've got 1 and 4. I've got 1 and 5. I can keep going. I've got 2 and 3. I've got 2 and 4. And there's a whole lot of combinations. I've got 1, 2, 3. I've got 2, 4, and 6. I've got 2, 5, and 6. I've got 3 and 7. There's way too many combinations for this. So what you can do is you can just say, well, hey, n is equal to 8, right? I've got 8 elements here. 1, 2, 3, 4, 5, 6, 7, 8. So number of subsets better be 2 to the n, which is 2 to the 8. And we could plug this into a calculator, and let's count 2, 4, 8, 16, 32, 64, 128, 256 we'd get right there. And obviously, like I said, this can be very annoying. I don't want to write out 256 subsets, but this is a very quick way of calculating how many there are. Just to be clear, number of proper subsets is equal to this 2 to the n minus 1. We get 255. I'll make that a different color as well so we can see that. There's always one less proper subset than subset. And there you go. That's going to be it on the subsets and proper subsets. And that's actually it for our lecture. Remember these formulas for the subsets and the proper subsets. Understand the difference between the subsets and the proper subsets, and then also we talked about complements as well. I'll flip back there just for a quick recap. That idea of universes, things that are not in the set but they're still in the universe. And I'll go ahead and leave it there for you guys, and I'll see you on the next lecture.